In this video, we're going to be concerned with a specific problem, counting the number of walks that connect two vertices. So suppose you have a graph, and you're not just interested in knowing if there is a walk connecting one vertex to another, but how many walks there are. Now, in an undirected graph, the answer is either going to be 0 or infinity, because if there is a walk connecting the vertex v1 to the vertex v2, then we could take the walk from v1 to v2, reverse it and go back to v1, then repeat the walk and go back to v2. This is technically a different walk from the one we started with, because it goes from v1 to v2 and then does some other stuff, but still ends at v2. So instead, we're not going to ask how many walks there are, we're going to ask a slightly different question. Given two vertices in a graph, how many walks of a certain length are there that connect them? So for example, take the graph below. 4 vertices and a collection of edges. How many walks are there of length 1 that connects vertex 1 to vertex 2? There's a single one, start at vertex 1 and then move to vertex 2. How many walks of length 1 are there that connect vertex 1 to vertex 3, however? There are none. These two vertices are connected. It is possible to walk from one to the other, but not with a walk of length 1. And how many walks are there of length 1 that connect vertex 3 to vertex 4? Because there are two different edges connecting them, there are in fact two different walks. I could take vertex 3 to vertex 4 this way, or I could take vertex 3 to vertex 4 that way, and those are two technically different walks. So we're going to make a matrix A in the following way. It's n by n, where n is the number of vertices in the graph, and we set Aij to be the quantity of edges that begin at vertex I and end at vertex j. So in an undirected graph, this graph is symmetric because the number of vertices going from vertex I to vertex j is the same as the number of vertices going from vertex j to vertex I. In a directed graph, however, it might be different. This matrix is called the adjacency matrix of the graph, and its entries count how many walks of length 1 start at vertex I and end at vertex j, because the entries are simply how many edges connect vertex I to vertex j. So the adjacency matrix of the graph above is now going to be given. So here it is. Notice that Aij is the number of edges connecting one graph to another. Vertex 1 connects to vertex 2, so A12 is 1. But there is an edge going from vertex 2 to vertex 1, so A21 is also 1. Down here we see that A43 and A34 are both 2 because there are two edges from vertex 3 to vertex 4 and two edges from vertex 4 to vertex 3. Now we're going to see how adjacency matrices help us solve the question of counting how many walks there are of a certain length. So the adjacency matrix shows which vertices are connected to which and with how many edges. Now if G is undirected, the matrix is symmetric, as already remarked. If G is simple, then every entry of the matrix is either 0 or 1, because we don't allow multiple edges between two vertices. So there's either 0 edges or 1 edge between two vertices. Loops in a graph show up as entries on the diagonal because these are edges that connect a vertex to itself. So that would correspond to some AII being non-zero. There is a loop from vertex I to itself. Now, how does this help us solve this problem that we've asked ourselves? How many walks are there of a certain length between two vertices? So consider how you might inductively count walks connecting vertex I to vertex j. As a base case, walks of length 1 are exactly given by the adjacency matrix. But now suppose I have a matrix B. For the sake of argument, the matrix B exactly tells you how many walks of length k begin at vertex I and vertex j. Instead of making entries of the matrix B correspond to edges, B sub ij is how many walks of length k go from vertex I to vertex j, and let's just assume we have this matrix. Now, how can we go about counting how many walks of length k plus 1 go between various vertices? So far what we've done is, we have an adjacency matrix A. A sub ij is the number of walks of length 1, in other words, edges, going from vertex I to vertex j. Now we've assumed inductively that we have a matrix B whose entries tell us how many walks of length k go from one vertex to another. Now to count walks of length k plus 1 going from vertex I to vertex j, we go through the following thought process. Maybe we have a length k walk that goes from vertex I to vertex 1, and then a single step going from vertex 1 to vertex j. Or maybe we have a length k walk going from vertex I to vertex 2, and then a single edge, a walk of length 1, that goes from vertex 2 to vertex j, and so forth and so forth. And maybe we have a walk of length k going from vertex I to vertex n, the last vertex in the list, and then a single step, a walk of length 1, going from vertex 1 to vertex j. So this can be counted in the following manner. What we have here is a following sum. B sub I1 is how many walks of length k go from vertex I to vertex 1, and then how many walks of length 1, given by the adjacency matrix, go from vertex 1 to vertex j. Or perhaps I could have done a length k walk from vertex I to vertex 2, and then a length 1 walk from vertex 2 to vertex j. Or, etc., or perhaps I did a length k walk from vertex I to vertex n, and then a length 1 walk from vertex n to vertex j. But what we've exactly done with this sum is computed the ith row and jth column of the product matrix B times A. Therefore, B times A as a matrix will give us exactly how many walks of length k plus 1 go between various vertices. So here we have the solution to our walk counting problem. Given a graph G with adjacency matrix A, the number of walks of length k connecting vertex I to vertex j is given by the entries of the kth power of the adjacency matrix. So the proof, for k equals 1, we're looking for walks of length 1, and this is exactly what the adjacency matrix does, as we've already discussed. Now let's assume that a to the k counts walks of length k connecting all the vertices. This is our inductive hypothesis. Then by our already existing argument, if I take that matrix that counts walks of length k, a to the k, and I multiply it on the right by the matrix A, what I end up with is the matrix that counts walks of length k plus 1. But of course, a to the k times a is just a to the k plus 1. Therefore, having assumed that the matrix a to the k counts walks of length k, we derive that a to the k plus 1 counts walks of length k plus 1. That's really all there is to the proof. So powers of the adjacency matrix exactly tell us how many walks of a given length start at one vertex and end at another. Now let's take a look at an example. In the graph below, the graph we saw at the beginning of the video, find the number of walks that begin at vertex 3 and end at vertex 1 using exactly 7 steps. So we make the adjacency matrix. We already saw this earlier in the video. It's a 4x4 matrix whose entries tell me how many edges go from vertex I to vertex j. We compute the 7th power of this matrix, which happens to be given as follows. And now, to find how many walks go from vertex 3 to vertex 1 of length 7, I look at the third row, first column of this matrix and get 146. There are 146 different walks of length 7 that go from vertex 3 to vertex 1. Let's take a look at another example. Here's a directed graph, and we want to find the number of walks from vertex 3 to vertex 1 exactly with 10 steps. Now we have to make the adjacency matrix. Here it is. Take a look that this is not a symmetric matrix anymore. For example, A3, 2 is 2. There are 2 edges going from vertex 3 to vertex 2, but there are no edges that go from vertex 2 to vertex 3. So A2, 3 is 0. Okay, so the entries here account for our directed graph. Now if I compute a to the 10th, okay, I've given it here. How many walks of length 10 begin at vertex 3 and end at vertex 1? We just need to find the third row, first column of this matrix, and here it is. There are 644 different walks of length 10 that begin at vertex 3 and end at vertex 1. And that's really all there is to it. To count walks of a given length going from one vertex to another in a graph, simply form the adjacency matrix and start taking powers.